Welcome to another demonstration of CustomExplorer Ultra. In this series we've looked at a number of features, but today we're going to be looking at using it as a regression environment for analog designs. My name is Paul Chapman. I'm an applications consultant with Synopsys in England. With a regression environment, you want the ability to test multiple designs with multiple tests and to collate your results in a useful manner, so ultimately your objective is to decide whether or not your chip is ready to tape out. What we're going to look at today is how CustomExplorer helps you do this. I've got just two designs that I'm going to be working with today. One of them is a driver that we've already configured and set up in the tool. The next one, which I'm about to set up, is an output driver. So I will call the design output. I'm going to read in the spice deck that defines that design, and I'm going to do an apply. As you can see on the panel there, there's a number of simulators that CustomExplorer supports. It supports all of the Synopsys simulators and increasingly a number of third-party simulators if that's what you wish to use. It does support netlists primarily, although we have links to schematic packages. They create a netlist and then load the netlist in the background. The reason for the preference for netlists is that, of course, is what the simulators are actually running. So by focusing on netlists, it means companies are able to use common version control systems to check that things have changed. If things have changed, that they're able to rerun tests as needed. And because the netlist is the source information for simulators, there's less risk that something's changed between the regression test that we're running here and the final tape out of your design. So, critical purpose of a regression environment is to answer the question, does the design work? In order to do that, you need to build a whole set of measurements of some sort to verify whether it's doing what you want. In this case, as I'm looking at an output driver, what I'm going to say is I'd like a peak-to-peak measurement of my output signal, which I'll drop in there. This design has a 2-volt supply, so I'd like at least 1.8 volt swing out of it, and I'll be a bit surprised and concerned if the output goes above 2.2 volts. Now, although you can see that creating a measurement like that is relatively straightforward, especially in a regression environment, you've probably got a predefined set of measurements that you want to do, and indeed the specifications that you want to meet. So with CustomExplorer, we can load those from an external file. After you've set up your measurements, you may well want to define a whole range of tests that will be run across perhaps a different set of load conditions, voltage conditions, and the like. If we come here, we find a little pull down that lets us find parameters that are present in the netlist that typically are the ones that we'll want to vary across the tests. So I'm just going to type in a range of values that we might want to consider. Let's have 500k and 10 megs for the output load. So we've got 3 values for each of these. If I click apply, the tool expands that list out into a complete set of tests. You can see here we've got 26 tests now. And in fact, we have a similar 26 tests for our driver. So we're ready to start running some results. Let's first enable all of them, and we'll kick them off. As you see, so we've got 52 tests, we've got a fair number of measurements going on. It's become a moderate sized job, and that's why we're using this form here, which is the simulation job control that talks to our compute farm. Whether you're using LSF or SunGrid or a proprietary load sharing set of software, this form enables you to understand which jobs have been kicked off, which are being queued, which are being completed. You can specify under the options file how many jobs you want going at one time, and if you have more jobs than you have queue slots available, this will work its way through your regression suite in a nice controlled manner so that you can control the number of machines, CPUs you're using, the number of licenses, and so on. Let's close that for the moment, because we can also see on the test list down here which have been submitted. Now what we're hoping is pretty soon we'll start getting some results, and indeed we've got things coming up saying success already. Now success in that context means the simulation actually ran and didn't give any errors that said there's nothing, no fundamental failure in it. If we look at the table now, you can still see some of these NF figures, which means that particular simulation hasn't finished, so now we're starting to do analysis while the simulations are still going on in the background. So we can see a little more. I'm going to turn off the design variables so we can see the full range of results. Wherever a measurement falls within the min and max that we specified, we get a green box, and so we don't need to individually read each result. We can say the green ones are good, the red ones, it came up with a number, but the number was outside the range that we wanted. If for some reason the measurement hasn't worked, perhaps the voltages haven't got to the right level, or some other reason like that, we'll either get an error or a not a number measurement, depending on the nature of the error. The important thing is, because it's a regression environment, what you want is it to press on, run all the simulations, and then come back with a summary of how things have gone. Typically regression environments, you'll be running, you might run it every night, you might run it every weekend. Once you've got a block in the design that you believe is good, you drop that design block into this regression environment, so as your SoC project progresses, your regressions get ever more involved as time goes on. Each block wants to get tested, each block gets tested in conjunction with other blocks. And then if you get those awkward things like a late change to the PDK comes in, or fill rules get changed, you need to rerun the whole design with different fill levels. This is where you come. You can change just one or two files, click, off you go, rerun, and everything's fairly easy to do. However, this being analog design, of course we're not going to believe the numbers alone. What we want to be able to see is waveforms. So how do we get to those? VTR18 here. Let's have a quick look. If we select that, we can come across and see highlighted in yellow are things where we can display a waveform from it. Easy enough to do in wave view. So there's our little sine wave that we're putting in as a stimulus. We want to see what that looks like when it's come out through our driver, and that's looking pretty good. It's nicely squared off, it's clipping, appropriately limiting, all very satisfactory indeed. Coming back to the results panel, we could perhaps come to number 8 there, where we can see a number of reds showing that things aren't quite the way we hoped. Again, select the output, display the waveform, and oh dear, that's a bit of a mess, isn't it? At first sight it looks like something very strange is happening on the top level. If you superimpose the waveforms there, you realise the real problem is it's just not getting up high enough, so it's not getting into the area where it's starting to saturate. And clearly this design needs a bit more work before we're able to tape out. So we've succeeded in running 26 corners on 2 different designs, collating all the results together onto this nice table, and it's telling us what the overall state of the design is. But if we were to get to the stage where, hopefully this is pretty much all green, maybe there's 1 or 2 that, might still be red, but you hope if you take it to a design review you can argue that it's close enough and get it signed off, then one of the things you'll want to do is to be able to document it in some sort of standard form of documentation. And for that, I've just clicked Save there, which has exported that table as a CSV file. If I pull it across the network, I can open it up in a standard Office tool, which would let me document things, fiddle, get things nicely presented, and so on. And I can go on and move this forward into taking it to a design review, where my peers can decide whether or not this design's good enough to be taped out. Given the amount of red on here, I think I've got some work to do on this design. But that wasn't the purpose of today. Today was to illustrate that with CustomExplorer Ultra, you can find this information, you can find it quickly, you can understand it quickly, which is just as important, and it allows you then to get back to focusing on the interesting bit of engineering and getting the job done. As I said at the start, this is one of a whole series of demonstrations that we're going to be doing of CustomExplorer Ultra. In future we'll be looking at how to set up mixed signal designs in this, how you can manipulate hierarchy using it, how you can run circuit check on it, and how with circuit check you can probe straight back through the netlists, ultimately to the schematics that generated the blocks. All of which enables you to get your design and your SoC out to tape out faster and more reliably than you have before. So we hope that you'll join us in future sessions. Thank you.